In this lesson, we're going to learn about solving a system of equations with two variables by using another method called the elimination method. Now, the purpose of this method is to try to eliminate one of the variables right away in this first step. And I'm going to give it a little example with numbers to show why this method would work. So let's say that you've got an expression on the left side of an equal sign, 5 plus 3, that's equal to 8. Well, this is a true statement. And we also have another true statement right below it, 4 plus 1 is equal to 5. So if I were to now add each of the left sides and the right sides together, I would get another true statement. So by combining numbers on the left side of an equation and combining numbers on the right side of the equation through addition, we're going to get another true statement. The reason why that's important is because if we look at this system of equations, notice that we would be able to add straight down by adding the like terms on the left and the like terms on the right. Since this is an equal sign, this indicates that x plus y is equal to 6 and x minus y is equal to 2. So these are both separately true statements. So since I see that the y values are already opposite values, I can simply add the results together. X plus x is 2x. And notice that y minus y cancels out. And therefore 6 plus 2 is equal to 8. So in this first step, we eliminated the y values, and therefore x is equal to 4. So now that we've got one of the variables that's going to make this system of equations true, we're going to be able to plug that value into either one of the original equations and solve for y. So if we now plug this answer back into either of the original equations, I'll plug it into the bottom equation. Then that simply gives us 4 minus y, which is equal to 2. And therefore, when I subtract 4 to get negative y equals negative 2, dividing by the negative 1 tells me that the y coordinate must be 2. So this is a completely different method, obviously, than graphing, because we never had to graph to find this solution or to find this point of intersection. And it's different from the substitution method in the sense that with the substitution, we had to isolate a variable and then plug that expression into the other equation. Now, we just simply added the equations together to eliminate the common variable. Therefore, the point of intersection is 4, 2. Well, in general, unfortunately, with most systems of equations, we're not going to see opposites. But what we would like to have happen is that there are opposites into both of the equations. For instance, maybe the top equation has a 2x and the bottom equation has a negative 2x. Or maybe see a negative 12y and a positive 12y. Or maybe a 15x and a negative 15x. So that's our goal, that's our objective. But when you take a look at any system of equation, we're not automatically going to have opposites. So what we would like to have happen before adding the left side of the equations and the right side of the equations is for the x terms to be opposites or the y terms to be opposites. So just to go through this process of the elimination method, I want to make sure that we're clear that we should always have the x terms stacked on top of each other and the y terms stacked on top of each other and the constants on the other side stacked on top of each other. The purpose for this is just to make sure that when I add the equations together, I'm adding like terms. So the first step that we're going to take here is that we're going to multiply either one equation or both equations by some number that's going to give me opposites. So taking a look at 2x and 9x, I'd like to find the least common multiple between those two values. So you can see that the common multiple between 2 and 9 is 18. So we'd like to multiply one equation, 2x, by 9 in order to get 18x, while the bottom equation would have to be multiplied by 2 to also get 18x. But notice we want opposites. So that's why we chose to multiply one of the two equations by a negative so that this becomes negative 18x and the second equation becomes positive 18x. So if we distribute that, that becomes negative 18x minus 27y equals positive 45, while the second one becomes positive 18x plus 10y equals positive 6. And now you should realize that the 18x and the negative 18x are opposites. So we can add these two equations together, and when we do so, that will eliminate this variable. Therefore, we're left with negative 17y equals 51, or equals 51. And when we divide by negative 17, we get that y is equal to negative 3. So now that we have one of the variables, we can take that value and plug it into any one of the equations. So I'm going to choose the top equation. So if we replace y with negative 3, then we get 2x minus 9 equals negative 5. And by moving everything around, adding 9 to get 4 and dividing by 2, we get that x is equal to 2. So my point of intersection is 2, negative 3. So anytime we don't have opposites, our goal is to force there to be opposites in order to cancel them out in the next step. Now notice that this would be a bad choice to use for substitution, or this system of equations. We wouldn't want to use substitution because none of our variables have a coefficient of 1. So if we wanted to use substitution, we'd have to get y by itself or get x by itself, and that would be pretty difficult to do without fractions. So that's why the elimination method will always avoid fractions, and we can now just cancel out the common terms. Now I'd like to demonstrate how we could have eliminated y's if we chose to, but in that sense, we'd have to look at 3y and 5y and realize that the least common multiple between 3 and 5 is 15. So to get 3y to become 15y, I'd have to multiply by 5. And in order to get 5y to become 15y, I'd have to multiply by 3. But notice that they have to be opposites, opposite signs, so I just chose to multiply the second one by negative. It doesn't matter which one you choose, you just need one of them to be a negative and one of them to be a positive, so that when I distribute the 5 to the top equation, I get this new equation. And when I distribute negative 3 to the bottom equation, I get this new equivalent equation. So notice that now the 15y and negative 15y are opposites. So we eliminated y first, while over in the original problem, I eliminated x first. And now we're left with negative 17x equals negative 34. Dividing by negative 17 gives me the x value first, when over here, we got the x value second. But now we take x equals 2 and plug it into either one of the original equations. I'll plug it into the top equation again, mainly because it's got smaller numbers to deal with, so I think it's going to be easier to solve for the other variable. So when I plug in 2 for x, I get 4 plus 3y equals negative 5. Subtract 4 and divide by 3, and we get y equals negative 3. So notice that by eliminating the x's first or the y's first, we're always going to get the same point of intersection, and we can always tell whether or not we're correct in our system of equations by plugging in the point of intersection, the x value and the y value, to both equations separately and solve.